Good day to you all. Alright, today's video is on electron configurations. Now, this is not a video that's going into the explanation of where all this comes from. It's just simply an application video. So as to where we're going to start is the fact that you're already supposed to know that there are 4 types of suborbitals in atoms. You're already supposed to be to this point. So there's 4 types of suborbitals: sp, ds, and f orbital. S orbital, a spherical orbital. There's one orientation of s, which is just referring back to that no matter how you turn that sphere, there's only one orientation of that s. Now, every orientation, every possible orientation can contain 2 electrons. So since there's one orientation, you can contain 2 electrons in s orbital. A p orbital, on the other hand, there are theoretically 3 possible quantum numbers for that, and therefore 3 orientations. In the case of P, I like to say roll, rock, roll, but anyway, it's PX, PY, and PZ. So 3 different orientations of this P orbital, and that is a hideously ugly looking P orbital. But anyway, that's for other videos. Now, every orientation, the PX can hold 2, the PY can hold 2 electrons, and the PZ can hold 2 electrons, one spinning clockwise, one counterclockwise. So that's a maximum of 6 electrons in a P. The d orbital, there are 5 different orientations. I'm not going to start naming them. They get kind of crazy. The d orientations, though, there's a total of 10 electrons you can hold in a d. And then there are 7 different orientations of f orbitals, and it can hold 14. Now, before you get into electron configurations and orbital diagrams and things, this has got to be lodged permanently into your brain. 1 type of S, 2 electrons, 3 types of P, 6, 5 Ds, 10, 7. So this has to be stuck into your head firmly. Now, we also need a little help from a chart as we do this. This is kind of important. If you're in college and you're watching this video planning on using this, you need to learn how to write this chart from scratch to use on tests. All right, so S is 1S. When you get to the second energy level, you can now have an S and a P. Whatever your quantum number is, your principal quantum numbers, that's how many sublevels you can have. When you get third energy level, you can have an S, a P, and a D. When you get to the fourth energy level, you can have an S, a P, a D, and an F. Hopefully I get all this fit on my paper. The fifth energy level, you can have an S, a P, and a D. And you're probably going, can't you have a 5F? And the answer is yes, you can. It's just that typically we don't get to atoms that are large enough unless they've been excited to actually get that big. And if you don't understand what it means to be excited, that means your electron, you goofy little computer, your electron is, and now my computer is frozen. Okay, so the electron has actually been bumped to higher energy level, or jump, transition, there, that's the word I was looking for. 7s. Now, it is very important as I do this that you draw good straight lines throughout all these. And I'm going to give me a little color on my lines here. So 1s, if you're doing this and mess up these lines, then you're going to therefore miss every question. That's how important drawing these lines are to this diagram. Let's see if I can undo that and make it one long straight line. And then the very last one. All right. What happens is this diagram, and this is how important this diagram is. You need it for pretty much everything you're doing. This diagram starts you out at the lowest energy. So the lowest possible energy is this 1s. And then the highest energy is this 7s orbital. And so what you need to do is follow each one of these arrows. This tells you your order. Every time you get to the end of one arrow, go back to the beginning of the next one and follow that one. This tells you this progression of energy. Because one of the biggest things that happens, you'll notice this. To begin with, it makes sense. 1s, 2s, 2p, 3s, 3p, But now all of a sudden you would expect after 3p to come 3d. Well, it doesn't. There's a little crossover here. It's 4s and then 3d, 4p, 5s, 4d. So you can kind of see it doesn't make just a complete linear progression here in terms of energy. So as we're doing these electron configurations, I encourage you to use this drawing. If you're in college, you'll probably have to copy this down on your own sheet of paper when the test begins. But hopefully you saw how to make it as I did it. It's not that hard. So let's just go straight in and do an electron configuration. And the first, let's just do like a really simple atom, like nitrogen maybe. So here we'll take the element nitrogen, and we're going to do an electron configuration. Well, to do that, I'm going to look at the periodic table, and nitrogen has atomic number of 7, which means it should have 7 electrons. So I'm going to use this chart that I've just written down, and I'm going to start doing this. So I'm going to start at 1s. It's known as the off-ball process. I'll start at 1s, and I'm going to give it 2 electrons. So an s can hold 2. There's one orientation of s, so it can hold 2 electrons. Well, give it 2, and now take that away from the 7, and that leaves us with 5 electrons. And after 1s comes, according to this chart, 2s is next. A 2s, other than being a larger version of an s orbital, it is an s orbital, which means it can only hold 2 electrons. A 7s can only hold 2 electrons. So that leaves us with 3 electrons. And we keep following. After 2s, come back here. Next is 2p. And a 2p, now there are 6 possible electrons you can put into a p orbital, but we only have 3 left, so we're going to give it 3. And that is actually your electron configuration. So this is the electron configuration. A lot of periodic tables actually have it on there, so you can even double check your answer to this. But this is an electron configuration. Now, I want to do something next. I want to do what's known as an orbital diagram next. Orbital diagram. So that's what I want to do next. Now, I'm just going to do diagrams for whatever came last. So I finished with 2p3. So I'm going to slip down here and I'm going to write 2p3 down. I'm going to do an orbital diagram for that. Now, depending on your teacher, it might be different in what they want on this, but this is what I want. There are 3 types of p orbitals. That's what we learned on that first page. There's px, py, and pz. So I'm going to draw 3 lines. Some teachers do boxes, some circles. It really doesn't matter. Now, there's 3 lines to represent. Again, what those lines represent? It represents that there's a px, a py, and pz. Now I'm going to do something. I've got 3 electrons. So now I'm going to distribute those 3 electrons, but there's a rule. And for some reason, I always think of a large, angry German lady, Hund's rule. Hund's rule says, I imagine her passing out candy at Halloween, maybe with sausage and sauerkraut in one hand. I don't know, but anyway, it's just an angry German woman. She's passing out Halloween candy, and she's saying, before anybody gets to everybody must have one. And that is a terrible German accent, and I apologize completely for it. But anyway, so everybody must have 1 before anybody gets 2. So I've got 3 electrons to pass out. So you get 1. Px gets an electron. Py gets an electron, and Pz gets an electron. And you're probably wondering, well, why are you drawing the arrows? It's just representing that those electrons have spin. And so those electrons have spin inside this atom. So one arrow represents clockwise, the other one's kind of representing counterclockwise. Now that's my orbital diagram. It's pretty much that easy. A p has 3 types of orbitals, and we had, once again, 3 electrons. And everybody, according to Hund's rule, must get 1 before anybody gets 2. So anyway, now I'm going to ask you another question. 4 questions. I'm going to ask you now for unpaired electrons, which is just saying how many electrons do you see without a buddy in this photo? Well, if you look up here, this guy, so there's 1, 2, and 3. None of those electrons have a buddy. In other words, they're all alone in their orbital. So I'm going to say there's 3 unpaired electrons in this. Now I'm also going to answer one more. What is your valence electrons? You see, most atoms want 8. It's called an octet rule to be stable. So we're going to get a little idea towards nitrogen stability here, and it's not. It needs a little help. But to do valence electrons, look at your highest N, as in 1, 2, 3, etc. So look in this problem up here. What is my greatest energy level? I've got a 1, a 2, and a 2. So my highest energy level is the 2. So how many electrons are in that 2? Well, there's a 2 and a 3. So there's a total of 5 electrons in that second energy level. So that's my valence electrons. Now, again, most atoms want 8. This one doesn't, so we know it's not exactly stable. It's not got this octet rule thing going for it. But it's also another thing here. You're going to probably wondering, why do we do all this? What's the significance of this px, this py, these orbitals that are left unfilled? Well, it actually tells us how this is going to bond. If you're in an organic chemistry class or something right now, you might be looking at nitrogen, and you're going to notice something. Nitrogen finishes, you've got a px, a py, and a pz orbital left, and each one's got 1 electron in it. Now, if you're in organic, you probably know this may be something like ammonia. Ammonia is NH3. It's a nitrogen bonded to 3 hydrogen atoms. Well, why would nitrogen want to bond to 3 hydrogen atoms? That's easy. It's because of these unpaired electrons up here. Nitrogen wants to somehow hook up and fill these orbitals. So it shares, like in the case of ammonia, it shares an electron with hydrogen. And what happens is this way, hydrogen actually has 2 electrons and it satisfies its needs, and ammonia satisfies its. And so this is the reason why we look at these orbitals so much. Let's go back up here and let's see if we've got this down. Let's do some more examples, and that's the best thing you can do. And if you want to stop watching this video, go ahead, because all I'm going to do is about 2 more examples at this point. So let's see. I'm going to erase all this. Let's do, didn't mean to erase quite everything. Got carried away with my erasing. Let's see. Unpaired electrons. Let's see. This was my electron configuration up here. So let's do another atom at this point, and we'll go through and answer these same questions. I don't know. I've got a periodic table in front of me here. How about, let's do sodium. So if we look at sodium, sodium has 11 electrons, and so we'll start doing our configuration. Sodium is, let's see, start with 1s, start at the lowest energy level. 1s can hold 2, which leaves you 9. Next is 2s, which can also hold 2, so that leaves us with 7. After 2s comes 2p on here. 2p can hold 6, and we've got 7, so we'll fill it up. And we've got 1 left. So after 2p is 3s. And a 3s can hold 2, but we've only got 1, so we'll just give it that 1. And we are finished. So that's my electron configuration. My orbital diagram, 3s. And since there is only a type of s, that means there's only one type of s orbital. I'm going to put 1 box. 1 line, 1 circle, 1 square. Here, I'll do a box this time. Some teachers like the boxes. So I'll put 1 box to represent that there's 1 orientation of S. And if you're still like, where are you getting this 1 orientation of S from? It goes right back here to the beginning. There's 1 orientation of S orbitals. So we'll go back and take a look at this. I've got a electron, so what I'm going to do is give 1 little half arrow up to represent 1 electron spinning inside the atom. Now, for my unpaireds, when I look at this, well, I only see 1 electron. He has no buddy, so my unpaireds is 1. My valences, I count 1, 2, 2, 3. Biggest number is a 3. How many's in it? 1. So my valence electrons are 1, and this atom is definitely not stable. As a matter of fact, this is going to make what's called an ionic bond. It's going to try and give away. It's going to be like, please, someone take this electron away from me. But anyway, all right. Now that we've done that one, dun, 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 let's do another one. I want to do a couple more. I probably ought to do at least one that's a little healthier, a little bit bigger. I don't want to. All right, let's do iron. We'll close it and shut it down on iron because iron is big enough. We're going to see some energy levels here. Iron's also a transition element, so when we do this, it may not match like an answer a periodic table might give you. So iron has 26 electrons. So here we go. You ready? I'm going to need a little more room, so I'm going to start here. Iron, start with 1s, 2, and that leaves you with 24. So S can hold 2. Next is 2s. 2s can also hold 2, which leads us with 22. After 2s is 2p. 2p can hold 6, which leads us with 16. After 2p was 3s. A 3s can hold 2, and that leaves us 14. After 3s comes 3p. 3p, a p can hold 6. So that leaves us with 8. We're finally getting somewhere. Let's see, after 3p comes 4s. And the S can hold 2. So that leaves us with 6. And then after 4s comes 3d. So here is 3d. Now a d can hold a maximum of, there's 5 orientations of d's. So it can hold 2 each. That's 10. But we've only got 6. Well, that's okay. It'll take all 6. So we'll stick them in there. And we are done with this configuration. And I'm looking at it, and hey, lo and behold, this actually matches my periodic table in front of me exactly. So that's great. For the orbital diagram, I'm going to go down here and look specifically at this 3d6 that I've just written down here. So there's my 3d6. Now this one ends in a d. Since this is a d, I'm going to give it 1, 2, 3, 4, 5 lines to represent 5 different orientations of D's. Now go back to what the angry German lady said. Everybody gets, and no, it's really not an angry German lady. It's just a joke. Everybody must get 1 before anybody gets 2. So everybody gets 1. Everybody gets 1. So everybody gets 1. So 1, 2, 3, 4, 5. But we've got 6, which means we actually get to go back and add another one here. And again, what this represents, the electrons in an atom, if you haven't seen it yet, have a spin. Those electrons are spinning. And so it's representing by the 2 arrows, one spins clockwise and one spins counterclockwise. So now let's go back. We need to do our unpaired on this. So if we look at this atom, there's 1, 2, 3, 4 unpaired electrons. So our unpaired is 4. Our valence is, go back up here, 1, 2, 2, 3, 3, 4, 3. Biggest number is a 4. And inside that 4, there are 2 electrons. And that is our valence electrons on that one. So we got a pretty good idea of everything here, I think, at this point. Only other thing I might do is I might go, what would you do if you had one finished with 3p5? How would your orbital diagram look? Well, it's a p. So you'd go, there's a px, py, pz again. You could do a circle, doesn't matter. Now, Hund's rule, there's 5. Everybody gets 1 before anybody gets 2. So there's 3, 4, and 5. So now how many unpaired electrons do you see? Just that guy. So your answer would be 1. Where y'all, man, my Alabama heritage shows through. What if you ended up with 3D3? Well, 3D3, you'd go do 1, 2, 3, 4, 5 to represent 5 types of D's, and then you'd go 1, 2, 3. Now, where the students tend to mess up is when you go to do your unpaired electrons, you go 1, 2, and 3, and y'all want to count these empty boxes. Well, those are just empty. There's nothing there. So your unpaired is just the 3 electrons you saw without a pair. Now, the only other question you might see, and I'll throw this in, it's a huge video, and it's covering like everything. Every now and then you'll see something give you a noble gas inner core. And all a noble gas inner core is, say for example, neon. If you do neon, neon's got 10 electrons, so it comes out to 1s2, 2s2, 2p6. So that is neon. No unpaired electrons, 8 valence electrons, meaning this thing's stable, stable, stable. So what somebody else might do then is come back magnesium. You might see somebody do this with magnesium. Magnesium is 1s2, 2s2, 2p6, 3s2. If you notice, it's very similar. Magnesium starts with this exact same phrasing, so you might see somebody do this on magnesium. Ne in blocks 3s2. And that's called a noble gas inner core. It's just a shorthand way. Since you've got the exact same beginning configuration, instead of writing it out, they just write this noble gas inner core, which lets you know it's that configuration. And if you remember, what's important anyway? What's telling us all this unpaired? This is telling us all the stuff we really want to know usually out here. So anyway, don't be surprised if you see a question about noble gas inner cores. 21-minute long video, but we have electron configured and orbital diagrammed our brains out. Thank y'all for watching. Have a pleasant turd-ferg day tomorrow. Bye.